So, good morning. I am Krishna Kumar. Back to Krishna's classroom. Today we look at a very powerful tool in the hands of analysts, namely the fixed point theorem. This is the most of the cases in PDE and ODE or in other areas, whenever you are encountering a problem of proving the existence of a solution of an equation, then this is a very handy tool. And it's, see, the attempt to find zeros of a function defined on some, say let us take f is defined on some interval a to b with some conditions like continuity and maybe some more restrictions, or it is defined on the whole interval minus infinity to plus infinity. We would like to ask the following question: does there exist any x where the function vanishes? Okay, that is, f is defined from R to R. We have put extra conditions. Ask the question: does there exist a point where x, where f of x is equal to 0? Very simple question. Let us assume, see, from R to R, if you define this function, now you can see that there are functions whose graph lie only in the upper half plane, and therefore it doesn't cross the real line at all. That means there are no zeros for this problem. For instance, you take a function e to the power x plus 1. This is what I mean. Take fx equal to, you know that the set of points lies in the upper half plane. Okay, so there exists no x such that, this you can easily prove. I mean, this is a smooth function. So, on the other hand, you take a function fx equal to some sin x. Obviously, it vanishes at x equal to 0, and it vanishes at several other points. So, there are several points which turn out to be the zeros of this function. Okay. So, there are a few questions here, like, obviously just continuity alone is not going to help you with this. You need some conditions on which it is, some more conditions to be imposed on f so that the function has a 0 x. Let us look at this problem. F is a map from zero. F is a continuous map from 0, 1 to 0. It is the interval, the closed bounded interval 0, 1 to 0. Now let us ask this question. Now we slightly modify this problem. Okay? We write the following. See, what does this mean? See, this function may have a 0 or may not have a 0, we don't know. But if it is bounded here, then this is true. Now let us remodify the problem. Okay, let me reword the question. Okay. What does this mean? If you look at the geometry of this problem, you are defining a map from 0, 1 to 0, 1. So the graph of the function x fx is something like this. It is defined on the entire 0, 1 and its range lies between 0 and 1 and it is continuous. Therefore, the graph is something like this. So, what is the question that you are asking? You take the function y equal to x, whose graph is this. It's given by the line which is a diagonal of the square. So this is xx. Now the question that you are asking is this: does there exist some value of x on this interval, say x1, where fx1 is equal to x1? In fact, you see that from the graph it looks there are so many points where this happens. For the function that I have drawn, there are so many points, say x1, x2, x3, x4, x5, where the function has the property that fx equal to x. Now let us do a little bit of drawing. So we know what do we mean by fx equal to x. This is the, so the question has been translated to the graph of fx crossing this line. Can you draw such that now the answer to this question is that if f is not continuous, there exist several functions whose graph does not cross the line y equal to x. For example, you can draw something like this. Something like this, with a discontinuity at the point x0. So if you drop the restriction of continuity, then you see that it may not have an intersection with the line y equal to x. Okay. So we have to get a general result, possibly one has to restrict it. Then you ask, suppose then does there exist such a function? Now, however hard you try to draw one and keep the graph here, then you see that if you want to keep it only in the upper portion, okay, the function is not equal to x. Certainly it cannot start from here. If it starts from here, the graph starts from here, then you see that there is a point where it intersects, so it starts slightly above, and then suppose the graph is continuous and drawn there, then you are left with something in the upper triangle, but not defined on the entire interval 0 to 1. Likewise, suppose you keep it negative also. Suppose you keep it the graph below this line also. That is, you are asking for a function defined on the interval 0 to 1, but it's not crossing this. I mean, it is crossing this line somewhere and continuous. Then you see that you may not be able to define it on the entire interval 0 to 1. Okay. There does not exist x belonging to 0, 1 does not exist x belonging to 0, 1 such that so you feel that the continuity is a necessary condition. Of course, discontinuous functions also may have the property that fx equal to x, that's a different thing, but you are talking about a whole class of functions, some property. So it appears the continuity restriction is a necessary condition if you want to make a statement on this. Okay, so it looks as though if f belongs to C01 and f is from 01 to 01, I want to venture a statement. So I try to give a formal proof for this. Okay. So one observes that if there are 2 points x1 and x2, x2, then by the intermediate value theorem, such that x is actually working on the function gx. Then it becomes a problem on the zeros of G. Okay. So you have Gx1 is greater than 0, Gx2 is less than 0, therefore there exists some point x in between. There may be several points, at least one point between x1 and x2 where the function takes the value 0 and that x turns out to be a solution of this problem. Okay, so we need to give a quick proof for this. Actually, the proof is contained here. Suppose what you do is you just use a contrapositive argument. Okay, suppose then what happens? f1 if at all it is defined. Is greater than 1. Okay, this is impossible. So the range of f is certainly less than or equal to lies between 0 and 1. Okay. Therefore, if you assume this, then the function is not defined on the whole interval 0 to 1, which is a contradiction. Likewise, zero at 0 and possibly by continuity in a that means the function is again not defined. It is a contradiction. It's a contradiction. Therefore, if f is continuous and defined from 0, 1 to 0, 1, then there exists some point, hence if fx is continuous, so that's a sort of general result that we have. Okay. And how to find such an f? We have a scheme that you can run. The scheme that you can run is this, which may be successful or may not be successful. It depends on the convergence of certain thing. So how do you approach to solve this or find the 0 or find the fixed point of f? Okay. So we can say that we mark X is called a fixed point of it's called a fixed point of X. So what you are proving is that given f continuous from 0 1 to 0 1, there exists a fixed point. So given X, given f and continuous, this is a version of the fixed point theorem. We shall investigate how do we find such a fixed point. Equivalently, you can see that it is the zero of a point. Now we also at the earlier problem I said, so our problem was in fact the interval 0 1 is just a choice. You can make it on any closed bounded interval 0 1. Okay, right. Therefore, let us ask the following question. So is it possible, if it is possible, to convert this question to a fixed point problem? Then we can apply the above result. This can be done in several ways. For example, define or if you write if G has a 0, see that if x1 is a fixed point of and vice versa. Therefore, the problem is essentially to convert this as a yeah. So if you are given a problem, given a function g, and you are searching for a 0 of this function, then you can define an f in the form gx plus x, so that a fixed point of f is a 0 of g. Okay, that is there are many ways in which you can do this, and in fact the way in which, see, if you want the fixed point theorem is to be applicable, then all these conditions will have to be done. That means it should be a map from some interval AB into the same interval. Then only you can apply this theorem. So all these things are required. So the question is, can you convert this into such a theorem? If you can transform it, then you can apply this theorem, get the result. Okay, so I'll just leave it there. Now, how to find a fixed point of a function f? That's quite simple. Okay. So one strategy to find a fixed point of x is this. Suppose you have you are searching for a if it exists. Okay. You know, you under conditions you have said that it exists really. So how to do? So one method is, look at this problem. You have this equation x equal to fx. Now you start with some x naught. Arbitrarily. Now what you can do is, you can define x1, you define as f of x0, and x1 is which belongs to 0, 1. There is no problem about that. Okay. Then what next? Repeat the process. You repeat the process and compute x2. As once again x2 belongs to 0 1. So f is defined. So you can work with x3 and so on. Assume xn is defined as xn is given as is computed somehow, then compute so you see, you start with some x0, keep recursively compute, thus zero 1 computed f starting from x0. Zero. So the question is this: is this sequence convergent? If yes, then the limit infinity belongs to 0 1. I am taking compact interval, therefore it does converge there itself. Okay. Then the question is, if yes, if it is true, then what we have is which is equal to, I can take the limit inside because f is a continuous function. By continuity, therefore okay, so such an x is a fixed point of f provided so that is something very interesting. So we have a way of finding it out, but there is a catch. You don't know whether the sequence is convergent or not. Okay, there are problems there, so let me just leave it there. So the problem now convergence of the sequence xn. But there is one argument that you can give immediately, that xn is bounded because it's on the interval 0, 1. So it's an infinite set of points. It's an infinite set of points on the interval 0, 1. So bounded set of points bounded by 1. Okay. So 0 less than or equal to xn less than or equal to 1. One can certainly say that since is bounded, and is compact, is compact, the limit of x and k is a point of. Now there is a problem here. The problem is this. Is this unique? There is only one. Does there exist only one fixed point for f? The answer to this question is not necessarily. Why? Because you see that every convergent subsequence, because this theorem does not guarantee that there is only one convergent subsequence or the sequence itself is convergent. Okay? It says there are convergent subsequences, and the limit of every such convergent subsequence will give you a fixed point. So the fixed points we have assumed. Now what I do is I strengthen the assumption. So let me additional assumption. The assumption is this, namely less than alpha strictly less than 1. Then of course you can easily see that if x1 and x2 are two such limits, and by the above assumption new condition which is less than this is a contradiction, because alpha is because of this condition. Okay. Therefore, you cannot have two such limits. There is only one and only one limit. So if we further assume that f satisfies this condition, then the limit of this sequence, I mean, that is there is the sequence xn converges, and there is exactly one point which becomes the fixed point of this theorem. Therefore, what is our theorem? And what is this condition? This condition is, see, you have f acting from 0, 1 to 0. Okay. Therefore, these are the image points of x1 and x2. The distance between the image points is strictly less than the distance between the points that you have started with. For every x and say x1 and x2 belonging to this is what is called contraction. So this is the contraction mapping principle. Okay. So the condition we have laid down assumes that f is a contraction. Okay. So that is something which we have assumed. So if your f has the additional property that it is a contraction, incidentally, when you assume it is a contraction, it implies f is continuous. So it's not an independent condition. So once you assume f is a contraction, map on 0, 1, then you have f has a unique fixed point. So there are two things that we have looked at. Many problems like finding the zeros of a function, if it can be meaningfully transformed to the search for a fixed point on some interval, okay, and you can prove that this is a contraction, then you are assured that there is exactly one fixed point for f. Okay, right? So that's a typical problem of this kind. We have come across this kind of problems even in other ranges from a completely different circumstances. So we take up this following problem from OD. Initial value problem. F is defined as a continuous function x and y. D assume to be open. That's assumption. And x naught, y naught, D. Now you see this is the region, this is the problem. This is D. Now what you can do is, yes, this S is contained in now by choosing A and B properly you can do that. Now what more you have? Choose, so you have now you choose H. Okay. F is bounded on S. S is a closed compact rectangle. Okay. F is bounded on S. Let M be the bound for S. Now define H by minimum of now consider the rectangle. What is it? R x y such that mod x minus x naught and clearly you see that R is contained in S. So it's a rectangle inside S. This is that we have considered, and R is some rectangle inside. So there are various, depending on the value that H takes, that is whether A is the minimum or B by M is the minimum, the shape of the rectangle will be different. But it is so. I am not going into the differential equation details of all this analysis, but what I want to do is the following. Okay. Then what happens? See that the first thing that you can prove is this. is a differentiable function it is said to be admissible if R so this is the terminology admissible. Okay, so that's a definition. So you see that if you are talking about the solution of the initial value problem, so if we are, so every solution IVT, that is this one. That is because then only you can compute f x y x. What is the solution? It's a differentiable function, therefore I can make sense. And this is a solution. Now what we observe is that there is an equivalent integral equation for this initial value problem. equation in the sense that every solution of 1 integral now this is something which you can easily see. Simple, because all that you need do is, let us write down what this integral equation is. Let me write down this. See, suppose then what we have is that phi derivative h this way and phi x naught equal to. Now you take the differential equation and integrate from x naught to x. See here, or we note that what you get is I mean all these operations are justified, and that gives you phi t and that is because phi x naught is y naught, that is phi is a solution of integral equation. And yx naught equal to, okay. The converse is also true, that if phi is the converse is that means you assume phi is a solution of this, which will give you this. When you see that phi is not only a continuous function, but it's also a differentiable function, because this is a constant and this is differentiable since f is continuous in its variables. So you have on the interval mod x minus x naught less than or equal to h. This is a differentiable function, therefore you can differentiate it, and you immediately see that phi derivative of x equal to f of x phi x. You will get back that. I easily verified that phi x naught is equal to y. Therefore, see that two equations are equivalent. That's a beautiful result. And this is going to be the crux of our problem. So we have transformed the initial value problem to an equivalent integral equation. I think if you have not read the book How to Solve It by Polya, okay, you should. Where he talks about transforming one problem into another problem, which the mathematicians often do while solving a problem. And this is a beautiful thing. We do it knowingly or unknowingly. We keep converting one problem into another problem. For instance, in the first case, finding the zeros of a function, we try to transform it into a problem like fx equal to x. Okay, so here we have transformed the initial value problem to an integral equation which are equivalent. Okay, now we make some observations. I am not going to write down the solution of this or how to prove the steps and so on. The earlier one I attempted because it's reasonably simple. Now what one can prove is this. Okay, look at this one, integral equation. Let's take up this integral equation. Okay. So you see that, let me define so what one can prove is the following. Suppose then y naught plus, that is a y this is quite easy to prove, because all that you need to prove is this. You want to estimate this, and this is less than or equal to, so that x r. That is why it is admissible. Secondly, if we start with a continuous function, now you see that ay is a differentiable function. Okay, so it's again it's easily shown that it's a continuous function. So everything is nice. So it's an admissible function. Therefore, that is not a worrying part. Okay. So you consider all. So consider C. And you define on this norm of y supremum for mod x minus x naught now you can say that this is finite. Okay, this is a then what you call x normed linear space and is complete. This is a major theorem. All continuous functions on the compact interval x naught minus h to x naught plus h with the sup norm is a complete normed linear space, which assures you that all Cauchy sequences on this are convergent. Now what do you do? Look at this. So you are interested in finding, so the question that you want to ask is this. So you see, because it is admissible, you see that A is now a map from x to x. That's easy to show because of the admissibility of y. So if you start with the admissible function, ay is also an admissible function. Secondly, you see that it's a compact interval on which you get a continuous function, or even you get a smoother function, differentiable function. So it is certainly the supremum exists, etc. So this is in that. Okay. Therefore, your question is this: the solution is essentially one nice question you are asking here. See, the Picard's approximation is the answer, because you see that Ax equal to Ay equal to y means this transforms into this equation. and that assures everything. Okay, so it is defined, y is defined on the interval mod x minus x naught less than or equal to h, y x naught equal to y naught, and y satisfies the differential equation, and therefore so we have transformed successfully our problem to a fixed point problem for some mapping. Okay, so you see that the problem is now with A defined as above. A defines a mapping from x to x. We are asking whether A has a fixed point. Okay, this is what Polya says. You take one problem, convert it into another problem, and you see, observe one thing. When we transformed this initial value problem to an integral equation, we have not solved it at all. We have only changed the language, and we have got another problem. What we said is this: if I can solve the transformed problem, then I have solved the original problem. Okay, so we successfully converted into a more amenable form, which we believe it is amenable, provided you can answer this question. And if you scan through the literature, which you would have seen, the Picard's approximation shows that this integral equation has a solution. In fact, that needs some work. I have only assumed f is continuous, but with f continuous, again, once again, the type of arguments that we have used, with some work you can show that there is a solution. Okay, I am not going into the details. And with further assumption, f is Lipschitz on R Lipschitz with respect to y. Now this we have proved, and I am not going into that. Those who are interested can go into this. But note that this is around the turn of, this was proved towards the end of century or in the beginning of the 20th century, because Picard from his days, and this was one of the prominent works by Picard to find an approximation to a solution using this idea. There again he used the same idea. He started with the constant function yx equal to y0. Then I iterated, he so he got a sequence. And then it immediately, using Lipschitz condition very effectively, convergence n to which turns out to be a solution of the so essentially the success came because he could convert this to a new problem which can be recast into the language of the fixed point theorem. Okay, and it's always enlightening to go through this. Now let me make some remarks, and then after that I'll prove the main theorem. Okay. Let me make a remark. The remark is this: your A, see, it's a machine. You have a machine constructed. Now, what is a machine? This is the A operation. A operation is what? You have, see, this is AY. So if you put in a Y here, then what you get here is AY. Okay, it goes through all sorts of operations inside and then finally come out like this. So it's like a machine where you can imagine that you start with y0, you get what you call y1, put it back, you get y2, put it back, you get y3 and so on. So you get a sequence of functions. At each stage it is refined through your machine. Okay, so this integral equation or this operation ay works as a machine which keeps refining the function. Okay, so you get a sequence of functions. Fine. So what you get? So what it produces is a sequence of functions. Now you are asking whether this function, this actually converges or not. Okay. So with some assumptions, you can show that this yn converges. So and limit n tending to infinity xs is a solution of the integral equation and hence that of initial value problem. So you see, long before these ideas came around, the technique was used in different circumstances. The same technique was used in different circumstances to solve the problem of finding a fixed point for an operator. So abstractly, what do you have? So abstractly, this is what we have in both the problems. You have a metric space, and in both the cases you have a complete metric space. So xd is complete. It's a complete metric space, and on that A is a map from x to x, which we assume A is a contraction. In the sense that the distance between AX, AY, AZ, that is the images, less than alpha times distance between. That means each stage the points start moving closer and closer. Okay, right? Because the distance between xn and xn plus 1 is bigger than the distance between xn plus 1 and xn plus 2. So they start getting closer and closer in the metric space. And of course this assures that A is a uniformly continuous function on x. So this implies A is a uniformly continuous function on x. Then what we can conclude from the analysis that we have done is that the equation AY unique solution okay. I think it is also nice to look at the geometry. See, this problem was in the air somewhere, but it became a popular problem sometime in the decade 1960 to 1970, or in some part of 1960. And then it became a sort of hotbed for research for many, and several fixed point theorems started emerging, because you see that by changing the various conditions you keep proving theorems. Even now I think there are people who indulge in that. You have a specific problem to handle, then you convert that into a fixed point problem. Okay, and some condition like the contraction mapping, something like that, to assure you that this is a unique solution. I mean, this is the general strategy. So there are a few things here. Given a problem, can you successfully convert it into a problem where this fixed point theorem language would work? Okay, and then what conditions you require to prove that there is a unique solution. Okay, so that is that. Now let me just give you some insight into the problem. Okay, so on R1 it is a map from 0 1 to 0 1 that we have considered. Now I will give a very nice example. Of course, this went round in the name coffee stirring problem in a popular language, and I believe there was an article which appeared in Scientific American sometime in the middle of the 60s, that is from between, say, somewhere around 1964 or 65 or 66. I am not very sure which volume it appeared, but you can always search for that. It's called as coffee stirring problem. So in the popular language it was worded as this: you have a coffee cup, coffee in, you stir it with a spoon, and then what happens is, on the surface all these points will get redistributed. The question that you ask is, does there exist one point which reach where it started initially, in the beginning? After making lot of travel, it finally settles down to the same point. This is not too appropriate, because some point can be considered as going inside or things like that, or you can raise all sorts of questions regarding the continuity, etc., etc. But this just gives you a specific case. But I think I can give you a better imagery. You would have seen the frame that we often use to keep the cloth fixed. Screw, etc. here. Okay, something like this. Then you clamp the cloth in it, and then you can see that this is the cloth clamp, and then you stitch here. Okay, this is the cloth. My drawing is not too perfect, but what you have is this: you have the two rings on which you clamp the cloth stretched, and then you use it for stitching. The whole purpose is just to make sure that the cloth does not move while you stitch something on it. Okay, so it's a useful thing. I don't know what it is called generally, but I am going to improvise this and then give you a example, make it an example for your fixed point theorem, or to drive home what the problem is. What you do is, you take a stretched rubber sheet which has elastic property, stretch it to some extent in all directions, and then clamp it in this so that it will remain in a stretched position. So initially you have something like this, This is the stretched position of the rubber sheet, and you mark that. Mark the boundary with a marker pen on the rubber sheet. After that, what you do? Just release it. When you release it, it contracts. So what happens? It will go into some shape like this, because you would have contracted. And points would have moved inside. Okay? So this is your x. You take this as your x. Now you see this you take as the transformation A. So A is a map which maps all the points here into from x to x. If you also see what we have done, because we have released it, and therefore what happens? You have the distance function is strictly less than some alpha times. That means the mapping that you have is a contraction mapping. 2 points move to 2 points there. The distance between them will be, so for instance, you take this point x and this point y. What will happen? This will move somewhere here, this will move somewhere here. So this is ax, this is ay, and the distance between them is smaller than the distance between. So this is your dxy, this is d of ax, ay. And you see that it contracts. That's why it's called a contraction mapping. Then what it says is that, then the theorem says that A has it says that there is exactly one point this is the fixed point here. So under the assumption of contraction, there is a unique fixed point. So this is the theorem that we are going to state, and I will suggest the proof of this. So let metric space, and if y is a contraction of x into itself, this is the abstract version. A unique this is the contraction mapping. It's a fixed point theorem. Now you see that there are several, as I said, there are several fixed point theorems that are available in the literature. This abstract version, and this is also sometimes called the Brouwer's fixed point theorem. It's one of the earliest version of this that you have. Now you see, we give a proof. Proof just follows the track that we have followed. Take any x naught denominator construct a sequence xn by the recurrence relation as I said, putting in the machine, okay, or refining it at each stage, you get a sequence. Now we first prove that xn is a Cauchy sequence. That is quite easy to prove because what you do is this, okay, because phi is a contraction, so what you have is that, see, observe that for every xy. That is a contraction constant that we have chosen is alpha, and alpha is less than 1. Now you observe that you can prove that d of equal to d of this is less than alpha which implies you can write this d xn x naught and add and subtract terms using triangular inequality, and eventually you have d. Now apply this with this inequality, therefore this is less than or equal to alpha to the power, sorry, I think this is not the one that I want to use. I calculate this. Now again apply repeatedly, so you get eventually this is less than or equal to This is true for now you write dxn xm is less than or equal to sigma you can check whether I am right or not. Check the terms. So this is less than or equal to minus 1 write everything in terms of x1 x0. Less than or equal to one minus alpha and this, since alpha is less than 1, since x is complete, it's a complete metric space. That is the assumption that we make. And then it is clearly x. Here we use phi is continuous. That is the justification for this. Okay. And phi is unique. So x is unique. If less than 1, and that implies hence okay. So this is a contradiction. So that completes the proof of the contraction mapping principle. It's a beautiful theorem, very powerful theorem, and you can see that in the theory of partial differential equations. On many places, wherever you have a problem of finding the existence of a solution and also a unique solution in some circumstances, this is a very powerful tool, because if you can somehow transform your problem to the language of the fixed point theorem and to a contraction map, then you are done. Thank you very much.